see here. Okay. I think we should be good here. Right. Okay. So, welcome once more, everyone, to another AP Calculus pre-response question run-through. Now, looking at the date here, looks like we really only have 3 more lives to go specifically on AP Calculus. Again, we have the actual test date on May 12th of this year, and just 2 more Mondays away from now. So, hopefully when we get everything through here, and we should be all the better for the type of practice that we're looking to do. Again, we're going over an old free response question packet from the College Board. I believe maybe on the next one we actually should be able to go through some multiple question perhaps. But for now, we have the 2015 free response questions that we will be going over. Again, as always, we'll be going through 2 questions at a time, and with all of the questions written out onto the notebook that we have here, so we can keep track of the question as we move along. Yes. Also, something we can do before we actually begin is, again, there's 6 questions, and they will be all graded out of 9 points. So we'll just go through all 6 of them, 4, 5, and 6, so that out of 54 available points, we can see what our totals will look like once we are through this exam. Okay, so I think with that, we should be good enough to go. Of course, as always, the first 2 problems will be done on the calculator on our very trusty TI-83 Plus, and we'll be going through, again, the problems 2 at a time for us to see how we can answer the questions as thoroughly as possible. As always, any questions that our viewers might have, you can send them directly through the chat or to the email down over there on that left side, the labcoatmath@gmail.com, and we should be good to go. So again, we'll be copying down the problems as we go through. The first 2 will be also be using a calculator, which we will be getting to once we get to those steps on this part of the exam. Okay, so let's begin with question number 1 on the 2015. Let's make sure we have that right. 2015 AP Calculus abbreviated FRQ for free response questions. Okay, so as always, again, the entirety of this recording will be on our main YouTube channel for those who are looking to go through it. Again, the steps, of course, are extremely important for any sort of free response section, because that's what they'll be looking at when we go over the answers. They are looking for specific steps to be completed in order for us to earn points. So let's begin with the context of the question. It tells us that the rate at which rainwater flows into a drain pipe is modeled by the function R of t being equal to 20 multiplied by the sine of t squared over 35. Okay, and this is going to be in cubic feet per hour. Okay, and then t is measured in the hours, and we have the interval going from 0 to 8 on t. Okay, and it tells us that the pipe is partially blocked. Okay, and with that being partially blocked here, allowing water to drain, out the other end of the pipe. At a rate of capital D of t for drainage being equal to negative 0.04 times t to the third power plus 0.4 t to the second power plus 0.96 times t. Okay. And then again, still for the same interval from 0 to 8 for t. Okay. And then they also tell us there is 30 cubic feet of water in the pipe at the t is equal to 0 mark. Okay, very good. So we have all of the context written out for this problem. So we can actually get on to part A here, where they're asking us how many cubic feet of water flow into the pipe during the 8-hour time interval from the 0 to 8 for t. Okay, good. So we get to our first section right here. Again, they want exactly just cubic feet of water instead of any sort of rate. Again, going from 0 to 8, which of course means that we have to do the definite integral, right? So if you want the net change in water, again, that's going to be instead the actual definite integral now, with the limits going from 0 to 8, because that is the time interval in which we're looking at this. Going for, again, they want to know only flowing into the pipe. They don't care exactly about anything of it leaving for the drainage. So that's going to be the R of t dt. So into the calculator. And because we followed those exact limits from 0 to 8 hours for the drainage pipe, again, because we're integrating the rate according to time, that will give us the net change in water from 0 to 8 hours. So into the calculator, we need to make sure we're going the definite integral 0 to 8 for the actual function 20 times sine of t squared over 35 and then dt. Okay, a little bit cut off there, but that should still be good enough for us, right? So we have to put the actual function inside of the calculator. And so with that, we'll try to follow that the best we can. So with the function integral operation right there, again, we need to put in the entirety of the function 20 times sine of t squared over 35. So let's go do that. So it's 20 times the sine of, we can use the variable t raised to the second power over 35. Okay, closing off that. And we need to mark it, of course, that this is for the variable of t, as that's what we're integrating by, going from the limits from 0 to 8 hours. Okay. So the entirety will then give us 76.570 if we round it to the third decimal place. So 76.570, and of course the units will be the cubic feet of water, right, flow into the pipe. Okay. So with that, that should be a very simple 1-point question if I remember this properly, because it's just a simple plug right into the calculator by knowing how to do a definite integral of a function. Then moving on to part B here, they're asking, is the amount of water in the pipe increasing or decreasing at time t is equal to 3 hours. Okay. And we need to give the reasoning as such. Okay, so if we're looking increasing or decreasing amount of water, right, again, that's just going to be the rate. Of course, we have the R of t. Again, this was going to be water into pipe, right? Well, on the other hand, the d of t, which they mentioned earlier in the problem, right, because it drains out because of the blockage there, will be water out of pipe, right? So as such, because these are both going to be rates, that will tell us whether we are increasing or decreasing in the total amount of water in the pipe as a simple difference or subtraction at the t is equal to 3 hours. So all we need to do is do a subtraction of the water entering at the 3rd hour and then the water leaving at the 3rd hour. And so with that, we should be able to get a positive or negative result. Of course, with positives being an increase in the amount of water, while the negative being a decrease in that instead. Right? So we can plug everything in so that we have everything ready inside of our calculator. It's 20 times sine of 3 to the 2nd power over 35, subtracted by the entirety of 0.04 of 3 to the 3rd power, then adding that with 0.4 of 3 to the 2nd power plus 0.96 times 3. And plugging 3's for the entirety of d of t right there. So with that, we have everything we need to then be plugged right into our calculator, making sure we're careful with that, so that we can then see what that looks like. So it's 20 times sine of 3 to the 2nd power divided by 35. Okay. All that then subtracted by 0.04 times 3 to the 3rd power. This calculator should be able to keep up with order of operations, again starting with the r of t and then moving down. 0.04 times 3 to the 3rd to the next step of the entirety 0.4 times 3 squared, and then plus the entirety 0.96 times 3. Okay. So with that, we have to make sure we have all of the signs properly. That's one thing that we could have gotten wrong. So we have a negative there on that side. Again, it's negative coefficient on the 0.04 after the subtraction. So let's make sure that is inserted there properly back here. So that instead of just 0.04 will be negative 0.04, and all the other coefficients line up properly. So we close it off and we get now the entirety of negative 0.314 if you round it properly. This is negative 0.314, and the units of course will be cubic feet per hour, because those are the units of r and d, those functions, in cubic feet per hour on each of them as well. Okay, so because we get this result with a negative number, right, so negative 3.14, this is going to be the note that the water in the pipe is decreasing at the t is equal to 3 hours. Okay, again, that is going to be important for us to note, again, as we specified the exact time in which this is happening. Okay. Again, this is just a comparison of rates. Of course, a negative number on the rate, meaning it's a decrease in the amount of water, with the positive being an increase instead. Okay. Moving on to part C, they're asking at what time t in the entire interval from 0 to 8 is the amount of water in the pipe at a minimum. Okay, so they're looking to see where it is going to be the minimum of the amount of water, meaning of course we're going to have to go do a little bit of analysis to see where the minimums are, right? So potential minimums. And then of course the word we like to use is candidates. Right? So we have the different times that we can look at, one of which will be the starting time and the ending time, so 0 and 8, because those could end up at minimums depending on the shape or the placement of the graph. But then we need to start looking at some local minimums, right? Which in this case is going to be looking at, right, again, we need to look at the rate being equal to 0 for that water. Okay. In any case though, the rate of course is exactly what we did in part B. That's going to be r of t adding into the pipe and then subtracted by d of t, the water leaving the pipe. And we need to see where we are going to cross the x-axis. Of course, we will look at this from the entirety from 0 going to 8 for the time frame, right? Because if we set this to crossing the x-axis, we can do our number line analysis to then see where some local minimums would occur as well. Okay, so because they're just looking for the time, well, yeah, we still need to look at the actual amounts too. So nonetheless, still, let's have a look at the actual graph itself. So again, this is going to be r of t minus d of t, so it's going to be 20. Let's clear that out first. So it's 20 multiplied by the sine of, now we have to switch it to x because we're graphing on the xy plane. So it'll be x squared divided by 35. Okay, so all that subtracted by the entirety of the negative 0.04 times x to the third power first. Okay, then adding it with 0.4 times x to the second power. Okay, and then lastly plus 0.96 times x on its own. Okay, so everything is written out just like that, and we make sure our window is set going from 0 to 10. I think that should be fine. We're just looking for some crosses as that contains the 0 to 8 that we need to go to. Okay, as you can see, we cross it only on one point, so let's see where that's going to be. So we can go ahead and calculate for a 0, and we move back across. We need to go on the left side of that crossing, and then tell that again on the right side, so that by narrowing it down, our calculator will tell us that when y is equal to 0, exactly on that point, we're looking at 3.272. 3.272. Okay, so at the 3.272 mark, as you can see on the actual graph itself, we are going from the negative sign of the rate of the positive side, right? So negative to positive on that difference of rates. And for us, that does make the most sense. Again, this is from going from negative to positive, right? All the negative rates decreasing, then suddenly going to an increase is going to be the actual relative minimum. Okay, so because of that, that's going to be another part in which we need to test that out in that sense. Okay, so now we need to actually look at to see where, right, that the amount of water is going to look like for us here. Okay, so again, the water is going to be instead the difference, right? So 0 up to a certain t. Again, so now we have to do this in terms of the amount of water entering, so r of t, and it's subtracted by d of t dt, right? This will tell us the amount of water, of course, keeping in mind that we did start with the plus 30 with the 30 cubic feet, again, starting at t is equal to 0, right? There's the amount of water in the pipe already to begin with, so we need to make sure we add that plus 30 in there. Okay, so with that, we can go ahead and start plugging in these in. Of course, at 0, we already know that one. That's the first one. That's already a freebie. Again, at the time 0, we're looking at 30 cubic feet of water in the pipe. But then let's see what we can look at towards the next ones at the 8-hour mark and then the 33.272 hour mark as well. Okay, so with this, we can run the actual same function integral here. And it's going to be r of t minus d of t. So it's going to be 20 times the sine of, let's see, t squared divided by 35. Okay, then we subtract that with the entirety of negative 0.04 times t to the third power plus 0.4 times t squared plus 0.96 times t. Okay, so all of this, right? So then this is going to be the r minus t function all inside of the integral. But then we need to tell it once more that this is going to be for the variable of t, going instead for the first part 0 to 8, right, on the hour mark. Okay, so because of that, we get all of 18.544 looks like. That's how many cubic feet of water are left. 544. Oh wait, hang on. Before we do that, actually, we need to remember we have to add the 30 to it, so instead that's going to be 48.544. Okay. Something to, of course, keep in note is that we have that 30 cubic feet to begin with, so we cannot forget to add that in, otherwise our answers will be incorrect. Then we can actually just run it once more in the previous time. Instead of 8 hours, it's going to be 3.272, so we did fill out that table. Again, at that local minimum point, we can see how much water is in there. We'll make sure we add that plus 30, just to make sure we get the right answer, again, of adding that 30 to begin with, and we get something lower at 27.965. Okay. So at 27.965, 0.965. This is going to be cubic feet, of course. Now this is going to be the smallest amount of water that is inside, or the minimum amount of water that is inside the pipe at the entire interval from 0 to 8. So with that, our work will show at t is equal to 3.272 hours. The amount of water in the pipe is at a minimum. Okay, and our work shows for it and how we found that. Again, looking through the relative minimum of the number line analysis of the difference of the two rates for that function. Okay, lastly, let's go to part D here. It tells us that the pipe can hold 50 cubic feet of water before overflowing. Okay, that tells us that for t is greater than 8, water continues to flow let's see, into and out of the pipe at the given rates until the pipe begins to overflow. Okay, then they're telling us to write, but do not solve an equation involving integrals that give the time W when the pipe begins to overflow. Alright, a little bit stretched on space here, but I think we should be alright. Okay, so just as a quick moment here, we're looking at the t being greater than 8, in which that we are looking to continue to flow until we hit that 50 cubic feet mark, right? And again, we need to give rates where the pipe begins to overflow at the time being equal to W. Okay, so with this, what we need to do, of course, is that we understand that if we're looking at 50 cubic feet of water, that must mean that we have to continue adding into this guy over here, right? Which, of course, is going to be, let's try to see, because we just keep going after the 50, so, and it keeps flowing in at the same rate until it begins to overflow. Yeah, so because this, we can actually, because it's exactly the same exact expression, we're going to go from 0 to W for the entirety of R of t minus dt of dt, so that, again, if we were to go look at the amount, again, we're looking to see, well, when it starts to overflow at time is equal to W, that's when 50 cubic feet of water are remained inside of the pipe itself. Okay, I believe that should just about do it for that, because we have gone close at the 8-hour mark. It just takes a little bit more for that to happen. Okay, so I think with that, that's all that we really needed to do, just as an understanding of how to reform the limit such that that will be the case. Okay, good. So that looks like that is all that is needed for the question number 1. I think if we did move the 50th aside, we could do that too. I wonder if that's something that they want to look for, because we could do, if you're looking to do it calculator wise, you would want to put it on the other side so that you could set equal to 0 and look at the cross. But in the case though, that's going to be the scenario for that. So let's go ahead and see what we're looking at for this next part here for question number 2. Okay, so question number 2, we have ourselves a graph here. So we have the point 0, 2 right there. Okay, and we have a second point, so coming across at 4, so 1, 2, 3, 4, and then all the way up at, actually let's go 1 and 2 right there, so we go 2 across there, and then we go up to 4, so we have the next point 2, 4 over there. That way everything can fit where it needs to, and we can get to our graphing here. So we have one part here which has the function like this, and then we have another function which goes straight curving like that. There you go. So that's region R right there, and then this is region S right there. Okay, so you have two regions coming from the intersections of two different graphs right there. Okay, then for this, they'll tell us that they want to let f and g be the functions defined by f of x being equal to 1 plus x plus e raised to the x squared minus 2x, and g of x, the other function now defined as, let's see if this will fit, x to the 4th minus 6.5x squared plus 6x plus 2. Okay, so then they'll tell us, continue that, let R and S be the two regions enclosed by f and g as on the graph. Okay, so we have ourselves this problem right here. Again, we have two functions listed out with the two regions that we're going to look at. So for part A, they will tell us first to find the sum of the areas of region R and S. Okay, so now we are looking at some of the actual, right, the total of the areas of those two regions. First off, of course, is that we need to understand that when we're looking at some sort of area for these two regions, we need to know the limits, and we need to know the top function minus the bottom function so we can plug them into the integral. And in this case will be dx because we can simply measure the heights between the two functions. So nonetheless, though, we still need to know the actual top and bottom functions for this graph here. So because this, right, something to note, of course, is that we have x to the 4th and then minus 6x to the 5th and so on, right? So we could actually graph it out too to get an idea, because this is still question number 2. So if we had a graph on hand here, we can quickly take a look at this first one, or f. So it's 1 plus the x plus e raised to the x to the 2nd power minus 2 times x. Okay, and let's take a look at the shape of this. And that kind of goes off on its own, so we're gonna have to change the window on that. Instead of going from -2 to positive, let's go to -1 maybe to positive like 8. And let's close off the x's down to like 5 because we don't need to go that far. Okay, so as you can see here with that shape of the graph, again, e of course being the function that will just continue to increase exponentially, right? Looks like this one underneath going around because they don't have a label for us, but the one, as you can see with the simple curve, is going to be f of x right there. And with the curling, again, because x to the 4th minus 6.5x squared, again, that's going to be the let's think these, because 4th power is going to be a quintic function, but nonetheless, because they're opposite signs on 4th and to the 2nd power, it should curve up and down because of that. So with this is going to be g of x written out right there. Okay, so because we need to find the areas of the two, right? Okay, so we need to add up regions R and S because of this, right? Something to know, of course, is that, as you can see, the curling g of x is on top from region R, while the region of S has g underneath of f as well, right? They switch positions between those two regions. So because of this, we then need to swap this out, right? First, knowing that it's going to be A to B, right? So B is going to be that intersection right there, which we'll find out in a little bit, which will contain the two, right? Then this will be the top function for the first part is going to be the graph of g of x subtracted by f of x dx. And then we need to add that with them from B all the way to C, or the end here, which is going to be x is equal to 2, as that 2 comma 4 indicates the end of that. Right? So B all the way to 2. For now, we swap it back to f of x minus g of x. Because from here, right, that curling f of x increasing on its own is indeed on top of g of x right there. Okay. So now because of this, we do need to find that actual B, again, B the intersection of f of x and g of x. And so by doing that, we can very easily look at some intersections by actually looking at the graph. So because we've already graphed the first part, the f of x earlier, we can just set up the next part, the g of x graph here. So this is going to be x then to the 4th power minus all of 6.5 times x to the 2nd power. Okay. Then added with 6 times x, and then lastly plus 2 at the end there. Okay. So with that then being the other function, we can go and graph the 2, and we get the same exact result that we have on our graph. But now with our calculator, we can actually go ahead and trace out an intersection so we can see the coordinates for when they will meet. So first curve that's close to intersection is going to be this one right there. Second curve, same thing. So with that, we can go and guess that intersection is going to be right there, as you can see, is the x coordinate of 1.033 if we round that properly, right? So it's going to be the coordinates 1.033 and the y coordinate of 2.401. Okay, and this will be on the calculator, as that will be definitely be, yeah, that one unfortunately will be easily done by hand. So the calculator tells us where the intersection happens, meaning that the area will then finally, when we set everything up here, is going to be going from 0 to the intersection of 1.033. Okay, for the g of x minus f of x, so that's going to be x to the 4th minus 6.5x squared plus 6x plus 2, then subtracted by all of 1 plus x plus e to the x squared minus 2x. Again, plugging in for the entirety of those two functions right there. Okay. Then lastly, we can finish this with add. Well, I think we should add at the bottom. So we can add the next part of the function, now going from 1.033, ending at 2. Now we're going to swap the location. So f of x will go first. So x plus e to the x squared minus 2x. Not dx. Sorry. We need to subtract that then, right? Because the f and g are swapped around because the function f is on top of g for region of S right there. So that's going to be x to the 4th minus 6.5x squared plus 6x plus 2 and dx like that. Okay, so we have everything lined up exactly where they should be, and we can then put this straight through our calculator to have a look. Okay. So let's see here. If we close out of that, so let's go ahead and run some integrals here. This time first, it's going to be g of x on top of f of x, so it's going to be now x to the 4th power minus all of 6.5 times x to the 2nd power. Okay, all that plus 6 times x plus 2, and then we subtract that with all of f of x, so it's 1 plus x plus e raised to the, now to the, let's see, x squared minus 2 times x power, and we close all that off. Okay, and then we run this for the variable of x here. Did we close everything that we needed to? Yeah, I think we did, yeah. Okay, then going from 0 to 1.033. Okay, so that is the first part of it, but then we can actually subtract, we'll add that with the, okay, add that for the region of S calculation. So we run another integral. This time we're inverting the order of this. So this is going to be 1 plus x plus e raised to the x squared minus 2 times x. Okay, so all of this now needs to then be, let's see if we close that off. Yeah, then be subtracted with all of the x to the fourth power subtracted by the 6.5 times x to the second power plus 6 times x plus 2. Okay, so with that, we will then tell the calculator that, we will close that off, and then we tell the calculator that we're doing this still for x, now going from the values of 1.033 all the way to positive 2. Okay, so with all that work, we end up with 2.004 as a result of the area. Again, plugging in just exactly what we have there. Took a little bit of time, but that's exactly what we need to do for us to find that total area between those two functions right there. Okay. I wonder if we could have done it a little bit differently if we just then subtracted it from the other side, but nonetheless though, that's what we have so far. And at least for this, that's the way that we can ensure that we've done both R and S for sure to be calculated for that area. Okay, then they're going to tell us next is that region S is the base of a solid whose cross sections that are perpendicular to the x-axis are squares. Okay, so then they want to tell us to find the volume of the solid. Okay, again, we're looking at volume for the solid whose cross sections perpendicular to the x-axis are going to be squares. Those are all the keywords that we're going to need to pay attention to, again, of course, for region S itself. So because we're dealing with region S, it looks like with a certain volume, this is going to be the integral for the bounds of region S, which we've done before already, so 1.033 all the way to positive 2. Okay, so with this, right, because we're going perpendicular to the x-axis, that just means that we can still do d of x, but of course the area of a square, it's just going to be the base of that square, right? And with the square, of course, base and height are exactly the same. So with the base being exactly squared, all we then need to do is go with the base itself, which us going from the top down from the region of S shows that, of course, g of x, which is the looping underneath, right? F of x is going to be on top of g of x, with the straight curve of f of x being on top of g right there. So we show that same relationship right there, right? If that's going to be the base of those squares coming across the region of S, we need to square all of that such that we can get the volume as a result. Okay, so with this, we can just substitute everything in there, so we can plug this directly into the calculator after setting up our volume integral right here. So it's going to be the entirety of f of x, which was the 1 plus x plus e raised to the x squared minus 2x. Okay, all this then subtracted, oh, you shouldn't have closed that, because this needs to be subtracted by now all of g of x, which is going to be x to the fourth minus 6.5 x squared plus 6x plus 2. And then all of this is going to be squared in terms of x right there. Okay. Right, so again, this is going to be f on the first part, g on the other part. Find out the base, squaring all that in the integral, giving us a volume as a result. Okay. So with this, this needs to be plugged in directly into our calculator here. So once more, with a function integral at the bottom right there, it's going to be making sure we put the parentheses at the start, because it's going to be all of 1 plus x plus e raised to the, it's going to be x to the second power minus 2 times x. Okay, so all of this then needs to be subtracted by the entirety of the function of g, so it's x to the fourth minus the entirety 6.5 times x to the second power plus 6 times x plus 2. Okay. So with all of that squared away, we're going to tell it to square all of that, because then again we need to make the squares and integrate across the axis, and then from the limits with the variable of x being defined from the values of 1.033 to positive 2 that we found out before. Okay, so with that we do get a volume of 1.283. Not too bad. Again, we're doing a very small section here and only of section S, so that does make sense to us that that is going to be the volume of that solid. Okay, very good. So let's finish off with part C right here. And that they're telling us to let h be the vertical distance between graphs F and G in region S. Okay, then they're going to ask us to find the rate at which h changes with respect to x when x is equal to 1.8. Okay, so we have h is the vertical distance between f and g. I think that's something that we should be able to find out pretty easily, but that's not what they're asking for. They want us to find the rate with h changing with respect to x at a specific point in time. Okay, so because we can first figure out what h is, right? H is going to be the distance, of course, so that's just going to be for the region of S again. That's going to be f, which is the function on top, subtracted by g, which loops underneath it. So that's f of x minus g of x in that sense. But again, they're not asking for h, they're asking for the change in h in respect to x at a specific x is equal to 1.8 point right there. Okay, so what that means, of course, is that we then need to be running some derivatives here. Again, this is going to be the derivative of f at 1.8 and then subtracted by the derivative of g at 1.8 as well. Okay, so because of this, we need to run some derivatives on both of them, which we can easily do with if we're looking to just simply plug in. Again, this can be done on calculator. That's the n derivative on the calculator I'm using, right? So n derivative, then going for plugging in f of x, and then at the 1.8 will then give us f prime of 1.8, right? And that will be done for g of x as well. Okay, so because of this, we can then conclude with our work here by plugging all that in, right? Sorry, x being equal to 1.8. We can then get the result after we run the two derivatives of f and then g, subtracted from each other. So in this case, it's going to be math 8, again, the function derivative operation on this calculator. First, we'll go on f of x, which is going to be 1 plus... Well, we can actually run this for both of them because derivative subtraction works for the entire thing. So this is going to be e raised to the x squared minus 2 times x. Okay. So this is going to be the function of f inside the derivative. Now we can subtract it with the function of g entirely. So this is x to the 4th power minus all of 6.5 times x to the 2nd power, okay, plus 6 times x plus 2. Okay, so with all of that already there, we can then tell the calculator that again, this is for the variable of x, but we are evaluating at 1 point because it's a derivative. There's only need 1 point, not the full range, because that's not what they're used for. And so we end up with the result of negative 3.812 if we round that properly. So negative 3.812. And this is going to be that result of the change in height in respect to x as it moves across the axis. At least that makes enough sense going across here again, because the height is decreasing obviously as we get closer and closer to the 2 mark on the x. Okay, so that will do for both parts 1 and 2 on this exam. So we should be able to go back and begin our corrections here. If we can pull that up really quickly, 2015. Okay, let's see if we can flip this back over here. Okay, so we have our results right here, and let's have a look to see what that compares to in the scoring guidelines themselves. Okay, so let me make sure we swap over to, let's do this. Make sure we get a nice color here. Okay, and there you go. Okay, that way we can go and highlight where we need to on this. Let's make it a little bit thicker there. There you go. Okay, so going back to question number 1, if I flip that back over. Again, question number 1 was dealing with that rainwater in the drain pipe there. Okay, and so with that, again, we have the R of t mentioned right there. Okay, as we move down, again, we have the D of t being draining of the pipe from the entire interval from 0 to 8. So with that, we can go ahead and take a look to see at part A. Again, they're asking for how many cubic feet of water is being it's flowed into it, which of course our setup right there, if we get our lovely red correcting pen here, is exactly how they want to set it up, right? The definite integral of R of t from 0 to 8 as shown. Okay, and then the result of the 76.570 cubic feet was exactly what they want to see. So again, the setup of the integral and the actual result will give us 2 out of 2 correct for part A. Okay, then they're moving down to part B here. So they're asking if is the amount of water increasing or decreasing at the specific time, which of course they need to set it up as exactly the difference of the two rates at the 3-hour mark, which is exactly what we did right there. And we get the result of the negative 0.313. Again, we rounded it to 3134 as part of our work, but that's going to be cubic feet per hour. Again, with that negative as a result, again, the water in the pipe will be decreasing because the net rate of the water in the pipe is a negative number, of course, being that water is being taken out of the pipe at that specific time, right? So with that showing, and of course the answer being correct at the negative 0.314, both of that will give us 2 out of 2 correct for part B. Okay. Then going onwards to part C, they were asking for the specific time in which it's going to be at a minimum amount, right? So again, because we're looking for a minimum, right, the water in the pipe being at a minimum as shown right there, we need to be able to show that from that time frame from 0 to t, again with the actual integral. That's exactly the way that I've shown on our setup, right? Adding 30 of course at the start because that's how much water was in there at the start. Okay, we need to go and see where first, of course, we have the candidates at the 0-hour mark and the 8-hour mark, again the start and finish, which are both exactly there, right? 40.544, both of them were correct as they were. But then we need to look at the rates and see where they're equal to 0, something exactly that we were able to do, again, on our side, in order to discover where the relative minimum was going to be. And at 3.272, right, that was exactly the time in which we will then check for that one, which we get the result of the 27.965, exactly the result of that. And so by comparing all three, the minimum, of course, was going to be at the 3.272 hour mark as well. Okay, so everything does line up exactly where they should with our 3 potential candidates, one each at the start and end point, and then lastly, one more point at the relative minimum after checking the rates and looking at the graph to see where it crosses the x-axis for that to be a possible relative minimum. So after all our work, we do show that from both the candidates and our actual answer, we get 3 out of 3 correct for that problem. Okay, and then lastly, for this, right? Oh, there is a little bit of a mistake that I kind of forgot here, right? Is that the integral is correct from 0 to w, right? This is all good. But of course, unfortunately, we needed to make sure that there's a plus 30. Again, that's at the time is equal to 0, that the amount of water was there to start with, if we want to see where we're going to end up with 50 cubic feet of water in the pipe. So unfortunately, because of that, right, so this 30, that was not there. That will ding me off 1 point. The integral is correct, but the actual equation is not. So this is 1 out of 2 correct. Very unfortunate that a very simple mistake was looked over on my end, because that plus 30 will for sure mark you off if you do not keep track of that 30 cubic feet of water that was in the pipe to begin with. So a little bit unfortunate, we stumbled a little bit at the end there, something that we easily should have gotten, but nonetheless, we move forward to see what we can do on the next parts, right? So 8 out of 9 for question number 1 on our record so far. And let's move to question number 2 before we move forward on this exam. Okay, so question number 2, we had those 2 graphs right there. Okay, and we have f of x and g of x listed out on the problem, right? So for part A, finding the sums of those areas, right, we do need to split it up into 2 separate integrals, of course, with the g of x being on top of the first one as shown right there in the answer, and then f of x being on top of the other. I used the letter B as the showing of the intersection, but they use the letter A. It wouldn't matter. And either way, we do end up with the right intersection at the point of 1.033. Again, they showed more decimal points, but the intersection does match properly where it should be. And so the answer of 2.004 is indeed going to be correct for what they need, right? So for both showing the integrals, the two separate ones, again, because we need to add them up based off of the switching in the which function was on top versus the one on the bottom, and the actual limits of getting the right intersection would all give us 4 out of 4 on part A. Okay. Moving on to part B, they wanted to know that the region S being turned into a volume, because we have a solid where we are going to be squares for that. So with that, we have the volume set up, of course, as such before as well, where we have the subtraction of F minus G because we're dealing with the area of S, and then going from the intersection all the way to positive 2 to encompass all of region S, except of course we need that squared right there, right? Because we are squaring a one dimension into the two dimensions and then getting the result of the area, or sorry, the result of the area and then integrating to get the volume. So everything was set up the way that it should have been, right, with all of that there, and we get the resulting volume of 1.283 as shown right there. Okay, so with this, right, with the right integral being shown with our right plugging of everything in and the answer of 1.283, that will give us 3 out of 3 correct for part B. And then lastly to part C, because we want to then find that vertical distance h, as shown right there, right? H is that vertical distance between the two graphs. We want to find the rate at which h changes with respect to x at a specific point, right? So with that, of course, we already know that h was going to be that difference as we listed down ourselves in our work. But then by looking at the change of h in respect to x, that's going to be the first derivative of f and g plugged in at 1.8. And so by doing that with our end derivative operation in our calculator, we end up with the correct answer of negative 3.812. So because both we have h of x shown properly as the derivative and then the plug-in, we get all 2 out of 2 correct on part C. Very good that we picked it back up on problem number 2 with everything there being correct across all the parts. So with that, that's going to be 9 out of 9 correct on question number 2. All right, so we should be good to head back over to the next portion of the exam, which questions 3 through 6. So the remaining of this exam will be a no calculator section. So again, we'll be putting away our calculators as the rest of these will not be allowed for us to then complete this exam. Okay. So as always, again, you can submit any questions through the chat or to the email labcoatmath@gmail.com as we move on to this next section of the exam. Okay, so question number 3 has a very nice table here, which we need to measure out in t in minutes, and then v of t, which is going to be meters per minute. Okay. And this table here has the points of 0, then 12, 20, 24, and then 40. Okay. And then the velocities then will be 0, 200, 240, negative 220, and 150. Okay, good. So we have the context of the problem, giving us that we have Joanna jogs along a straight path. Okay. Then for the entire interval from 0 to 40, Joanna's velocity, v of t, is given on the table. Okay. And it shows there all that we have as the data points that they gave us. So going to part A, it's telling us to use the data in the table to estimate the value of v prime of 16. Okay. So if we're estimating a derivative of a function that we only have some selected points for, this is of course going to be an average rate of change. rate of change type of problem, where we need to look at to see which 2 points will be the best, right? To see where we can find a possible first derivative, right, between the 2 points, which with if we're dealing with 16, it looks like between, right, 12 and 20, with 16 being right in between there, with 16 being 4 more of 12 and 4 less of 20. That would exactly be the case here. So with the average rate of change equation, that's going to be v of 20 minus v of 12 over the 2 x values there of 20 minus 12. Again, this can approximate v prime of 16 for us. Then with a simple plug in from the table itself, right, across those values. So with v of 20 being 240, subtracted by v of 12 of positive 200, and the difference being 8 here, it's going to be positive 40 divided by 8, giving us 5. Now, if you want to look at the actual units here, right, again, we're doing the meters per minute on the numerator, but we're dividing it once more by minutes as a difference between 20 and 12 minutes on the denominator, giving us the, if I can actually do that properly, so it's meters per minute squared. Oh, that does not look proper, so let's try that one more time. So that's going to be 5 meters per minute squared, if we can show our units properly. And that will be the result of us approximating the first derivative of v between those 2 points using average rate of change. Okay. So that's going to be part A. Then they'll tell us next to using correct units. Explain the meaning of the definite integral and we're integrating from 0 to 40 of the absolute value of v of t dt in the context of the problem. Okay, and then they're going to tell us also to continue to approximate the value of the integral from 0 to 40 absolute value of v of t dt using a right Riemann sum with 4 subintervals. All right, so we have our work set out in front of us like that. Okay, so when we're dealing with the absolute value integral of velocity, right, what our minds need to understand, of course, with the absolute value being shown right there, this is going to be the total distance traveled equation. Right? That's what we're looking at. Because we've taken the absolute value, we don't take into any account the negative signs for the actual velocity function, right? Meaning we don't care about the direction in which he's going, but we add up all the distances with the integral, again, without any regard to the direction. We're just trying to see what the total amount that, in our case, Joanna has traveled. So, right, this integral then, so that's a value v of t dt, is the total distance that Joanna travels from 0 to 40 minutes. Okay, so let's get on then. All right, if that's going to be the actual result of this, then let's get to the actual Riemann sum. All right, so it's a right Riemann sum. Of course, with the equation, with being a Riemann sum, is going to be the area of rectangles going across, right? So again, the area is going to be equal to, again, just a simple base multiplied by a height. Okay? With right Riemann sums, of course, meaning that if we have the table of 5 graphs, 5 points right here, with 4 subintervals that they were asking for at the start of the problem, that means we're going to use the right-hand side, right? Those 3 values. But of course, making sure that the negatives do not qualify because we are in the absolute value. We have to swap that over once we start adding it all up. Okay, so because of this, right, the base, of course, is going to be the difference between the 2 points on T, and the height's only going to be using these 4 starting at 200 and ending at 150. So with this, the total area will then be described with the first base being 12 and the height then being 200. Okay, adding that with the next base being the difference between 20 and 12 and the height there being 240. The third rectangle is going to be the difference between 24 and 20. And then this time though, because 24 and 20, those two are contained the negative 220 point. Remember, it's going to be a positive 220 because we are in the absolute value. Again, total distance, we don't keep track of those negative signs. We just keep it at the height of 220. And lastly, finishing it at the difference between 40 and 24, and the last height being 150. Yeah. So all this needs just a little bit of extra working through with a little bit of algebra, and we should be good to go here. So 12 times the 200 right there is going to be 2400. Then adding it with 8 multiplied by 240, that should be, was it the 1920? Right? Keeping track of those numbers moving along. Then we have a positive 4 times 220, so that's 880. And then lastly, with a distance of, let's see, this will be a distance of 16 and 150. Well, that's going to be, well, starting with a 900 and a 1,000 afterwards. Sorry, a 900 and then a 1,500. So if you do a little bit of work here, so it's 900 in the first part, then 15 times 10, yeah, 1,500. Yep, so that's going to be 2,400 on the last rectangle. All right, just a little bit of work here on that side. Again, no calculators allowed, just a little bit of our mind to work out these numbers here. Then, by calculating all of that up there for these 4 rectangles, 2 2400s makes it 4,800. And then the 1920, 1880 is going to give us, what, a flat 2,800. Okay, then finishing this up at 7,600. And this is going to be the meters that she has traveled, right, entirely across that time frame from 0 to 40 minutes. Okay. Then going on to part C here, telling us that Bob is riding his bicycle along the same path. Okay. For that time interval, 0 to t now going to 10, Bob's velocity is modeled by b of t being equal to t to the third minus 6t squared plus 300. That's going to be his equation, and telling us where t is in minutes and b of t is in the same meters per minute. Okay, but then they want to tell us to find Bob's acceleration at the t is equal to 5 mark. Okay, so because we're doing acceleration, of course, acceleration at any given time is going to be the first derivative of Bob's velocity. So as such, we need to run the first derivative of that b of t equation right there, giving us 3t squared minus 12t, and the 300 going straight off to 0. Okay, so with that, then we just got to plug in for 5 into that equation, giving us 3 times 5 squared minus 12 times 5, giving us 3 times 25, and then subtracted by 60, then giving us 75 minus 60, then giving us 15, and because it's acceleration, we're going up another tick on the time in the denominator, so that's 15 meters per minute squared that Bob is traveling by at the 5-minute mark. Okay, then lastly on part D here, it says that based off of the b of t on part C, okay, they want us to find Bob's average velocity on the interval from 0 to 10. All right, so if they're asking then instead for average velocity. Again, this is going to be using the average value function, right? Because we have the BFT. Again, the BFT already is velocity at any given time, right? That means the average value for that velocity is going to be 1 over 10 minus 0, right? 1 over that interval of time that we're looking at. And then we run it through the definite integral from the same interval, 0 to 10, of that b of t. Okay? So with that, we can get this set up quite nicely with 1 over 10 multiplied by that integral with the function t to the third minus 6t squared plus 300. Okay? Then we run the actual integral itself. So that's going to be 1/4 t to the fourth minus the 2t to the third power plus 300t. All this will then be evaluated from 0 to 10. Okay. So that is set up the way that it needs to. And so we can run the actual integral limits itself. So 1 to 10. And with 10 coming across and 0, of course, zeroing out the entirety of that equation, we just end up with 1/4. Again, 10 to the fourth is going to be 10,000 minus 2, t to the third is 1,000. And then 300 plus t is going to be 3,000. Okay. With the 1/10 coming across the entirety of this, this will cancel out at least 1 0 across all of them. Okay. And then 4 divided by 1,000 is going to be 250, subtracted by the 2 times 100 now is 200, and then the 300 waiting on that side. Okay, so this ends up at 350. Again, this is meters per minute. Right? Again, this is the average rate at which Bob is moving down on his bike, right, at this rate. Okay, so that should wrap it up for part 3 on this exam. Again, a fair few basic ideas here about how to know the relationship between velocity and acceleration and things of that sort. Okay, so it looks like with problem number 4 we'll get started, but it looks like one of the problems needs to be done on the packet. Yeah, let's do the one with that, but let's see. First we're going to consider the differential equation. We have dy over dx being equal to 2x minus y right there. Okay, now a will be done on the packet. Okay, as this is going to be, right, for that differential equation, the packet is shown to have a slope field which we will need to fill out. Okay, tells us that on the axis provided, you want to sketch a slope field for the equation at the 6 points provided, right? 3 over there, 3 over there. Okay, so we need to do a bit of work here of running the equation across for all these points. Okay, I think here maybe a table will be in order here. I think that might be best here. So we run all the points here for x and y and the resulting dy over dx. Right, so going across for x, well, we can go into 2 rows. So if x was 0 for 3 points and y was -1, then +1 and +2, and then another case where x is all 1s for those 3 points, and the same repeat, -1, +1, +2. We can then list out the slopes across each of them and fill out the slope field here. Okay, so x being equal to 0 and y being equal to -1, that's going to be +1 on that. Then x being equal to 0, y being +1 is -1, and then -2 on that. Then with x being 1, that's going to be 2 plus a +1 there, so +3. Again, we're referring back to the 2x minus y on that first derivative for us to fill this out. Okay, then +2 minus 1 is going to be +1, and +2 minus a +2 is going to be 0. Okay, so with all of this now filled on the table, we just need to transfer it over into the actual slope field graph right there. So at 0, -1 down there is going to be +1 slope right there. 0, +1 is going to be -1 slope right there. And 0, +2 is a -2 slope, so something like this. Okay. Then going back at +1, -1 right there is +3, so we get a pretty high slope right there. and then 1 comma 1 is positive 1 right there, and the 1 comma 2 is going to be 0 right there. Okay, so not too bad. Just that help of a table will be quite nice for us to follow along with each point, and that will be good enough for part A. Then on part B, for this same problem here, they want us to find the d squared y over dx squared in terms of x and y. Okay. Then it continues that we want to determine the concavity of all solution curves for the given differential equation in quadrant 2. Okay, very interesting. Nonetheless, though, we have our work set out for us in the first point here, that we need to find the second derivative of this equation, right, for the differential equation starting with 2x minus y. So again, if this is the first derivative, dy over dx of 2x minus y, then we need to do another implicit differentiation of the second derivative, meaning that the 2x goes to a positive 2, and then the y goes back to a dy over dx, which, again, by taking the derivative of y, will go to dy over dx as such. And so we just need to plug everything back in for the dy over dx, so it's 2x minus y inside of there. And with a little bit of a cleanup, that gives us the second derivative of this equation to 2 plus y minus 2x, arranging it as such. Okay. All right. Okay, so 2 plus y minus 2x right there. Okay. But then if you're looking at quadrant 2 for concavity, because quadrant 2 means that x is going to be less than 0 and y is greater than 0, right, for those results being in quadrant 2. So with that, we need to then realize, right, if we were dealing with concavity, right, the idea is that if the second derivative is greater than 0, that's going to be concave up, and if that second derivative is less than 0, that'll be concave down. Okay, so with all these rules in mind and the following results, because x is less than 0, right, so given that we have 2 and then y is supposed to be a positive number, so we're adding a positive number the entire time in the y section, and we're subtracting by x, 2x, which is going to be a negative on another negative number. That means it's going to be just all positives being added up, right, because we're subtracting a negative on that last bit right there. So because of that, right, the concavity to the equation in quadrant 2 is always up, right? Because we've shown that because x is less than 0 the entire time and y is greater than 0 for the entirety of quadrant 2, we are always going to be concave up as a result of the second derivative always being positive during and any points being inside of that quadrant. Okay, moving into part C, they're going to tell us to let y be equal to f of x. Then we need to find the particular solution to the differential equation with initial condition the f of 2 being equal to 3. Okay. Ah, yes. Well, we have a viewer coming in. We have Dig VJ, if I pronounce it correctly. Yeah, we have a high schoolers giving us their support. Yes, thank you for letting us know that you are enjoying the stream. Right, this is indeed the AP test, at least in what we're doing here, right, is going to be a national test in the United States for people usually in high school that are taking this exam. And so hopefully this, again, is a good way to follow along with the types of math that we are doing for this exam that's actually coming up within just 2 weeks. So again, yeah, thank you for your support, and we definitely hope to see you in future live streams as well. All right, So because we're looking to solve an initial equation for this differential equation with that initial condition right there, okay, they're still going to finish off here. They're going to ask that, does f have a relative minimum, maximum, or neither at x is equal to 2. Okay. Well, something to note, of course, is that specifically at this, we do need to know both x and y. So, right, so at x is equal to 2, and let's see here, because it's, yeah, because we have that right there, 2, 3. Yeah, so at the point 2, 3, right, because they gave us already the 2, 3 already in the start of the problem, right, we can actually go look back at the first derivative, right? So this is where x is equal to 2, y is equal to 3. So if you plug that in there, right, plugging 2 into x and then 3 into y for that first equation that we have already, we get a result of positive 1, right? And because of this, right, f, we can already finish the first part of the problem, where f has neither a minimum or maximum at x is equal to 2, because the dy over dx at x equals 2 is 1, right? Again, we need this equal to be equal to 0 for us to then determine if it's going to be a minimum or maximum on this graph. Okay, so moving forward though, we still have to deal with that first part of looking for the original function. So because we have this set up here already for the first part of this example, again, we're going to need to let's see. We actually don't need to find it. No, it's not our job to actually find it. Just kidding. That's actually, the question itself is shown already, right? Because we've done the analysis already, right? At the point of 2, 3 on this first derivative, right? Again, because it was set to equal to 1 instead of 0, we can conclude that it will be neither a minimum or maximum, because the first derivative must be equal to 0, right? So must be 0 if we were to have a minimum or maximum as a result of that. Okay. Lastly, let's go to part D here. It tells us to find the values of the constants m and b, for which the solution y is equal to mx plus b is a solution to the differential equation. Okay. So we will need to go ahead and start looking at, right, this actual equation right here, right? If we're going y equals mx plus b on this guy, which in our case though, right, because we're dealing with the fact that we're looking at a linear line here, okay, and if this being a solution differential equation, this means that, again, if y is equal to f of x, and that m is going to be the slope, in this case is supposed to be that first derivative of the equation dy over dx, and we still have the point as well, f of 2 being equal to 3 is our point that we're looking at. We can then set this up as such, right? So given that we have y is equal to the slope of dy over dx already set up as the 2x minus y multiplied by x plus b. Okay, I wonder how we can get this set up here, because we have already the equation of 2x minus y already there. Right, with it being already a solution. Okay, yeah, so because we already have this as dy over dx, right, and because we have the points right there, right, m is going to be the slope at the 2, 3 point, meaning, right, from what we've done before as part of our work, we can evaluate for the slope at the x is equal to 2 and y is equal to 3 as they were done before. Right, so plugging this back in to the original starting differential equation of 2x minus y. So it's 2 times 2 minus 3 as a result, giving us a slope of 1. Right, that's going to give us a slope of 1 on that. Okay, so starting that, so y is equal to 1 times x plus b. But then because we need to know that this crosses that point of 2 comma 3 on that point, we need to plug that in back into this equation that we were working on. So 3, 2 in the x plus b. So therefore, b must be equal to positive 1. Again, m is also equal to positive 1 as a result of all of that work, right? So the actual solution tells y is equal to x plus 1 as a result of this work here. Okay. And that will be a possible solution to the differential equation that we started with. Okay, very good. So with that, we have our solution set right there. Okay, and there we can go back to our, because this is problem number 4. Again, we solved 2 problems at a time. So this is going to, we're going to correct problems 3 and 4 together to see what our score will look like on this exam itself. Okay, so let's go and switch the screen back over here. Okay, so moving back, again, we're dealing with question number 3 now, what we dealt with earlier. Okay, and we have that table right there of the values as Joanna was jogging in that straight path. So with part A, they're asking to see the estimated value of v prime of 16. V prime of 16, of course, is going to be used with the average rate of change between 20 and 12, right? As was the case here, right? So because we did the difference of the 240 minus 200, again, those are the points from 12 to 20, looking at the change of the values of v over t is exactly what they have set up right there. So 5 meters per minute squared was exactly what they needed to see for us with that setup there to get 2 out of 2 correct, or just 1, sorry, 1 correct. 1 point out of 1 for part A. Something very simple and straightforward to just look at average rate of change to approximate the first derivative. Yep. Then moving on to part B, they want us to be able to explain the meaning of that integral. So the 0 to 40 absolute value of v of t dt. And then we need to use a right Riemann sum of 4 subintervals then to approximate that actual value itself. Okay. So again, because we understood that by taking the absolute value of a function inside of an integral, right? For velocity, that means that we are looking at total distance, because again, we're integrating the absolute value of velocity to go back to distance. But keeping track of the absolute value means that we have total distance, not caring about the negative signs on the velocity. We just want to see the total amount that was traveled by Joanna from that entire interval. Okay, so again, us showing this, right, is total distance traveled from 0 to 40 minutes. That's exactly what they want to see as the first explanation. Then moving forth with the Riemann sum here, right, is that we then add everything up here, right, base times height, going across all 4 different rectangles, right? So again, as shown right there, we have our 4 rectangles of the Riemann sum using the right side equations, right, right side heights of the 200, 240, 220, and 150, keeping sure that this is a positive 220 because we're doing the absolute value of those results on velocity, right? And so the negatives go back to positive, giving us a total of 7,600 meters. That's exactly what they want to see, right? So both the explanation, setup of the Riemann sum, and the answer of 7,600 will give us all 3 out of 3 correct for part C. Part B, that is, part B for this problem. Okay. Then part C will continue that we have Bob that's riding his bicycle from 0 to 10. And we have his velocity written out like that, okay? So then we need to find the acceleration though at a specific time from that velocity equation, right? So again, because we need to take the derivative of the equation of B, right, in order to find the acceleration that Bob is looking at, we get 3t squared minus 12t, right? So B prime of t, again, is going to be correct for us to get the first point. And then by plugging in 5 after that sense, we get 15 meters per minute squared, right? Exactly what we need to on that side. So that's both 2 out of 2 correct for setting up the first derivative and then plugging in for 5 to get the acceleration. Then lastly, at part D, to finish this off here, right? We want to find Bob's average velocity from that same time frame, right? Average velocity, of course, meaning that we have to go then multiply by that coefficient, 1 over 10, right? To be dividing it by the actual time interval going across for Bob's velocity equation, right? By running the actual integral, right? Putting it all through the work there, right? Of integrating and then getting the actual limits to be plugged back in, we do get the proper 350 meters per minute as the average velocity, as was shown right there. Okay. So again, first, of course, of setting up the integral, running the actual integration, and running the limits to get our answer. All three of those will give us 3 out of 3 correct for part D. And we've gotten everything correct, no points missing. So what that means for us is going to be that for question number 3, we get 9 out of 9 correct on that as well. Okay, our record looking pretty okay so far. So let's go over to question number 4 to see how we matched up over there. Okay, so at question number 4 here, right? Again, we had that differential equation dy over dx being equal to 2x minus y. So at part A is going to be looking at the actual slopes, which we had to do on the packet, right, directly, so we can write over those parts right there. So again, part A was going to be this section right here, making sure we have the slopes where x is equal to 0, right? We have 1 right there on that point. That's exactly what we want to see, right? And then again, we have the 2 negatives going downwards right there, and then the 2 positives, and then the other positive right there. Again, we're equal to 1 on those 2 points where they need to be. So with that, all that does match up properly, as is on the answer key for the slope field to be filled out by us. So this is going to be 2 out of 2 correct on part A, with everything matching up where they need to. Okay. Then going on to part B, they asked us to find the second derivative for that differential equation, right? So running it through, right, the second derivative by plugging everything in, right, is 2 minus dy over dx. Then replacing the dy over dx back into terms of x and y will give us 2 plus y minus 2x, right? The order's a little bit different there, but everything matches up exactly what they need to. Okay, so that's going to be 1 point showing that up. But then they asked to see in quadrant 2, right, whether we can determine the concavity for all those solution curves. Okay, so we could, because of the fact that x is less than 0 and y is greater than 0 in quadrant 2, as shown in our work, we can show that it will always be concave up for all of quadrant 2 as shown in this answer, right, because of us locating where all those signs will change. So because of that, we get 2 out of 2 correct on both analysis of the second derivative and the concavity in all possible solution curves in quadrant 2. Okay, moving down to part C here, right? Okay, we then do show that it is neither a minimum or maximum at x is equal to 2, right? It's going to be neither, because our work does show that by plugging in for the derivative there, we get a slope of 1. If we want a min or max, we need to have a slope of 0 for that to be the case. That is not going to be, because again, by plugging the 2, 3 as part of the points that they gave us, it was neither in that case. Okay, so because our work and our justification are both correct, that's going to be 2 out of 2 correct for part C. Okay. And then finishing up for part B, part D. Oh yes, I believe there's going to be some issues on this, right? I think if I remember how to do this one properly, is because we had to then do the actual derivative here. So why don't we redo part D here on this side here, because that does not match up with exactly what we're needed to do here. Okay, so because we needed to do the possible, right, we needed to find M and B, right? This is going to be a solution to the differential equation. Again, the wording unfortunately is not the best in my opinion, but nonetheless though, should be no excuse for how to be able to solve this. Meaning that we have to, if we want to set this up as y equals mx plus b, right? If we wanted to see that the slope was going to be the dy over dx in that sense, okay, we then needed to go and take the first derivative of the entire function so that we can match it as such. So that means dy over dx is equal to, then from there, right, the entirety of the derivative of x. So that's going to be, if you remember here from this side of things here, They did a very interesting note here. You know, let's try to backtrack here for a second. So let's actually switch back to the actual camera so we can get this done properly here. The main issue, of course, that I personally don't like the wording on this, but that's just neither here nor there. What we need to do here is that we need to show that if we're looking at y equals mx plus b, again, we need to isolate for that slope of m in order for us to get the slope of this done correctly, meaning that this is going to be the entirety of... I'm trying to think about this because this still doesn't match exactly the way that I'd like to. But nonetheless though, so yeah, but if we took that first derivative, right, so the dy over dx is equal to then the entire derivative of mx plus b, right? Because this is going to be the derivative on both sides of the equation, that must mean that it's going to be the entirety well, that still doesn't make enough sense to me right now to be able to explain that properly. But yes, still nonetheless, so that's going to be the slope, which because we're dealing with the slope of dy over dx, we can substitute back in the 2x minus y for that first differential equation that we dealt with at the beginning. Okay, so if this is going to be the case, right, the slope itself, right, could then be isolated on its part. Yeah, so showing that we have y again on that side of things right there, where we can substitute back the 2x minus the entirety of mx plus b, right, still being equal to m on that side. Okay, then by running back a few isolations here, is that we get 2x minus mx minus b is equal to m. Then we can move everything onto its own side, right, so that we get 2x minus b is equal to m plus mx. Then we can factor out the factor of m, so it's to be 1 plus x. And so m is going to be equal to 2x minus b over 1 plus x right there. Okay. And so with that, let's see here. No, that doesn't add up either. Oh, yeah, this is a really weird problem because they don't really ask this very often anymore. So the idea being that if we move this down here, so for this line it works at 2x minus b, and then if we subtracted it with the m minus mx is equal to 0, we can then isolate out that 2x minus b, then subtracted by all of m of 1 plus x must be equal to 0. Okay. Yeah, so we'll then group that up in the sense that when x is equal to 2, right, because that was the point that was given to us, right, we get 4 minus b minus m times 3 is equal to 0. So in that case, right, we get the final solution that m is equal to positive 2 and then b is equal to negative 2 for those two to be able to match into there. Again, not exactly a very good problem, I would say. Again, this is not exactly something that's going to be asked for, but nonetheless, though, we unfortunately missed it because of the wording, but we'll have to try again next time to see if we can get this all done properly. So, you know what? Just to make sure that we're on the same page about this, I'm going to actually redo it exactly on the packet itself so that we have a record to see what we're having to deal with over here. Okay. So again, we're dealing with part D, where we're dealing with, they want to see find the values of constants m and b so that this equation y equals mx plus b is a solution to the differential equation. Okay, so if we're going to do part D, again, this is y is equal to mx plus b written out right there. Again, this is going to be a solution for dy over dx. Okay, so because we need to get it in the form of dy over dx, right, we need to then take the entire derivative in terms of x for this entire equation. Right, so with that, we will get then dy over dx being equal to the first derivative of mx plus b. Okay, and so by doing that, right, we will then realize that, right, this is still equal to, right, d over dx being the slope of this equation, okay, which again we can plug back in, so that's gonna be mx plus b, again all this first derivative being equal to the 2x minus y, right? That's from the beginning of the dy over dx as such. And so the first derivative of mx plus b is just going to be the actual slope itself of m being equal to 2x minus y. Okay. And so because of that, right, because we already have y already listed out from our previous equation, so it's a little back and forth with our substitutions here. But because we have y already equal to mx plus b, we can substitute that back in there from that first derivative. So subtracted by all of mx plus b like that. Okay. And so because of this, right, we can go ahead and then subtract out. So this is going to be 0 is equal to 2x minus mx minus b minus another m. And we can group up all of the terms of m on one side and leave the rest out on the other. So then 0 must be equal to 2x minus b, also not subtracted by, if we factor out the negative, that's mx plus m on that side. And then we can then factor out an m of x plus 1 right there. Okay. So with that, right, we can then conclude that because this must be equal to 0, okay, right, because that must be equal to 0 along that side. Okay, let's see here. So I'm trying to think, because the reason why is because the entirety of no, they actually didn't do it that way. They did it a little bit different. So let's backtrack from there. They grouped it a little bit differently. They grouped the x's to one side and then the b minus m on the other, right? So because of this, this is going to be a 0 being equal to the x factored out on the one side, giving us 2 minus m on one, and then subtracted by all of b plus m on the other. Okay, good. So because of this, right, because this needs to be equal to 0, this entirety must be equal to 0, which means m must be equal to positive 2, and therefore b must be equal to negative 2, because again, m is equal to negative b. On that relationship, again, those two groups must be equal to 0 on that side. Okay. Again, I personally wouldn't have liked this much either. Again, this problem actually does not show up any longer, I would say, on this type of equation or type of exam, just because the wording isn't very good or the line of work very clear for this. But nonetheless, that's going to be what is required. And unfortunately, we do miss a few points off of that, giving us only 6 out of 9 correct on question number 4 because of part D. Nonetheless, though, we'll have to make do. Again, everything else seemed to be good, the types of questions that they would ask for. So with that, we should be able to move on to question number 5 and 6 to finish out this exam. Yep. So we have question number 5 right here. Okay, and we have the entire graph that we need to copy down. Let's see, something like this. Across 2, go 1, 2, 3, and 4. Okay. So you come across, you go across 3. So we go across like this. Then we go down and we touch at 1, and then we go back up and we touch again at 4. So this is gonna be graph of f prime. Let's set it right there. Okay. So again, it will tell us that the function f is twice differentiable. Okay. And then on the interval going from -3 to +4. Okay. Then they told us that f prime has horizontal tangents. Tangents at x is equal to -1, x equal to +1, and x equal to +3. Okay. Then it tells us that the areas of the regions bounded by the x-axis, okay, and f prime on the intervals from -2 to +1 is equal to 9, and then from +1 to 4 is equal to 12. Okay, they give us some areas to work with, which is quite nice on their part, but we'll see what it looks like for us on the actual problems themselves. Okay, moving to part A, they'll tell us to find all x coordinates, okay, at which f has a relative minimum. Okay. Relative minimum, of course, means that we need to find where f prime of x crosses from the negative side to the positive side, right? And crossing from negative to positive is the definitive way of finding a relative minimum. And in this case, because we have, why did it say minimum? What the, this is maximum. That's a little bit unfortunate. I did copy that down wrong, but it's a maximum instead. So we're going to swap that around. So instead of crossing from negative to positive, this is going to be crossing from a positive into a negative value. Again, for the first derivative, which we do have the graph of, which we do have exactly the point of -2, or we cross from the positive side to the negative side for that first derivative. Okay. So because of this, right, the f has a relative maximum at x is equal to -2. Again, evident already on the graph. This is going to be a single pointer. Again, our explanation is good enough that we're crossing from positive to negative on the first derivative, enough to us to mathematically prove that we are dealing with a relative maximum there. Okay. Part B asks on what open interval what intervals contained in -3 to x to +4 is the graph of f both concave down and decreasing. Okay. All right. So because we need to make sure that we're both concave down and decreasing for the graph of f, that means that if we are concave down, that definitely means that the second derivative of f must be less than 0 as a result of that. Okay, and then decreasing, of course, would mean that the first derivative of f must also be less than 0. Okay, so with that, we need to show that both of those would be the case between from -3 to +4 for the entire section right there. Okay, and because we only have the graph of f prime, again, this part is going to be easy, right? Decreasing, of course, is just means that we have to be less than 0 or underneath the axis. So that means we go from -2 all the way to +1, because at +1 we touch the x-axis right there. But then we can continue forth and go from +1 all the way to +4. Okay? That's the interval in which we're decreasing, but that doesn't mean that we're necessarily concave down there, right? Which means, in our case, if we're looking for the second derivative to be less than 0, that must mean that the first derivative is decreasing. Right? We need to make sure that we understand the relationship between the first and second derivative, because if the first derivative is decreasing, that means that the second derivative will be less than 0, right? The second derivative meaning that it's the slope of the first derivative. So with that, we have the decreasing from -3 all the way to -1 as it increases after that point, right? So in -1, it hits that 0 tangent and moves up. But from -1 all the way to +3, again, we hit the other negative, like the negative down to the horizontal tangent. So we have our two intervals here from -3 all the way to -1, and then from +1 to +3. Okay. So we have those two intervals, but then we need to look at where they're all coinciding, which if you look here, right, we cut it off at, so let me see the graph of f is concave down and decreasing from, now we can go in this case from -2 because that cuts it off from -3, right, all the way up to -1 only. All right, so going to -1 on the x, and right, because that will cut it off for the concave down, right? Doesn't matter if it's decreasing any longer because the concave down is cut off. Then it resumes again at +1 all the way up to +3. Okay, and that will be the case for this graph. It's a little bit of a test of understanding what concavity and decreasing is going to be if we're only given the first derivative of the graph. Okay, then part C tells us to find the x-coordinate, coordinates of all points of inflection for the graph of f. Okay, and we need to give a reason as such. Okay, points of inflection, of course, means that this is going to be the second derivative must be equal to 0. Okay, and of course the way that we know that is that if the first derivative has a 0 tangent, right? In other words, of course, is going to be a max or min on the first derivative graph. Okay? Thankfully, they already gave us 0 tangents, or again, the horizontal tangent, already at the start of the problem, right? Again, that the first derivative, it tells us here at the start of the problem, the first derivative f prime has horizontal tangents at x is equal to -1, +1, and +3, right? All of which have those horizontal tangent lines going across them. Again, showcasing that that will be the case for the first derivative, which then translates over to the second derivative, having a result of 0 for a point of inflection. Okay, so at x is equal to -1, +1, and +3, okay, right, f has a point of inflection. Okay, and that'll do it for that, right? Well, we've shown that that was going to be the case across those 3 points. Okay. Then on part D, it's going to tell us that given that f of 1 is equal to 3, write an expression for f of x that involves an integral, okay. Then for that, find f of 4 and f of -2. Okay, so we have an original point, f of 1 being equal to 3, and again, we still only have the first derivative to work with. We have no equation, nor do we have anything else in that sense. But because we want to see an expression that involves an integral, we have to set it up as such, right? So if you want to find f of 4, right, knowing that we have to bring back our good old friend, fundamental theorem of calculus, noting that, of course, if we ran the integral from +1 to +4 on the first derivative in respect to x, right, fundamental theorem will then dictate that we are dealing with the difference of f of +4 minus f of +1. Okay, and because you want to isolate for f of 4, that would mean that f of 4 is equal to f of 1 added to the other side from 1 to 4 f prime of x dx. Okay, that's our first scenario right there. Then going forth, if you want to find f of negative 2, we'd have to actually swap it around because we are dealing with the negative 2 to positive 1 f prime of x dx. Okay, because again, we need to go from lower to higher on those limits right there. But the issue is, of course, that we're going to rotate that around. So we can actually swap it around to, again, so using fundamental theorem of calculus, of going from a negative version from, well, that necessarily wouldn't work either. No, let's just keep it as such because it'll be a lot easier to solve if you would do it by hand. Again, fundamental theorem will then show that it's f of 1 minus f of negative 2. Okay. Then with a little bit of swapping around, f of negative 2 from that line of work by moving it over to the right side and the whole entire integral over to the right side from the left, we will then show that it's going to be f of 1 now subtracted by the entirety from negative 2 to positive 1 f prime of x dx. Okay, and that should do it for problem number 5, as we have dealt with exactly what we needed to, right, for these 2 points across all these parts. Okay, so we should go on downwards to question number 6, and we should conclude this packet. Okay, so finishing up here, we have question number 6. They're telling us to consider the curve, the y cubed minus x times y is equal to 2, and then it tells us that it can be shown that the dy over dx being equal to y all divided by 3y squared minus x. Okay. So we have an original equation as well as a differential equation that results from there. Okay. Then going on to part A, to get us started for this, they want us to tell us to write an equation for the line tangent to the curve at the point -1, +1. Okay, so if you want a line tangent, of course, we're going to need this to be y is equal to m of x plus h minus it's minus h plus k. Okay, right, again, this is the point slope form of a tangent line, where of course h comma k is equal to the -1 comma +1 that they gave us already. But of course the m is going to be that slope, right, d over dx, evaluated at the -1 comma +1 that they gave us earlier. Okay, so that way we can find the slope at a very specific point for this curve. So by plugging everything, we get 1 over 3 times 1 squared minus a -1 right there. There's 1 over 3 plus 1, giving us 1 over 4. Okay, so with that, we can plug everything together. Y is equal to 1 over 4 of x plus 1, because we're subtracting by -1, plus 1 on the outside. Okay, and this will be the equation of that tangent line at that specific point. Pretty easy setup and a pretty easy question to get us started on part A. Okay, then it tells us to find the coordinates of all points on the curve at which the line tangent. Let's make sure we swap over on that. Okay. So that tells us that the line tangent to the curve is vertical. All right. So with this, right, if we're looking for a tangent line, right, line tangent that is vertical, this of course means that the dy over dx must be equal to some number over 0, right? With the number over 0, of course, that would mean that we have an undefined or a vertical line, and then this vertical tangent line as a result of that. Okay, So because of this, right, we need to take a look back at the entirety of the first derivative, right? So this is the result, which of course means that 3y squared minus x must be equal to 0, right? If this was the first derivative, okay? So this being the case, we can then substitute back or move everything over that x is equal to 3y squared, right? But of course, it doesn't really give us any points. It just tells us the relationship between the two. Now, of course, if we want to see if any of these can fit inside of the curve itself, we need to go back to the original equation, right? So equation of curve is going to be y to the third minus x times y being equal to 2. Okay? So that we can now solve for all of the y values if we plug in the 3y squared where x was, meaning that we get y to the third minus 3y squared times y being equal to positive 2. Okay, so as a result here, we can complete our work here with y to the third minus 3y to the third being equal to positive 2, with this being negative 2y to the third being equal to positive 2. So y to the third being equal to negative 1. Y must be equal to negative 1 if that's going to be, in any case, a possible vertical line tangent. Okay, so with this, we have to plug that back in, right? So the x being equal to 3 times negative 1 squared. So x will be equal to positive 3. Okay, after that plugged in, so the only point really is negative 1 comma positive 3. And just to be sure, let's see if this does match up exactly with the curve, right? So back to curve. Again, to check. Right, so back to our original equation of the curve right there, we get the 3 to the third minus negative 1 times a positive 3 should be equal to positive 2. Okay, this is actually the wrong order. No, this needs to be positive 3 comma negative 1, right? So let's not do that. Let's make sure we plug everything properly. Instead, this is negative 1 to the third minus a 3 times a negative 1 should be equal to positive 2. So with this, that's negative 1 plus a 3, which is equal to positive 2. That does check out. So it looks like this is the only point that's available, 3 comma negative 1, which in that case will be a vertical line tangent to that curve. Okay, our work checks out. So let's go over last theta part C to finish this all off here. It tells us that we want to evaluate the second derivative of d squared y over dx squared at the point the negative 1 and positive 1 as a result. Okay, so if we want to do the second derivative, of course, that means you have to go to the first derivative. So y over 3y squared minus x, and we need to take all this and take one more derivative of that. Okay, and keep a track of all implicit differentiation rules. Again, this of course means that we have to do quotient rule first, right? And we'll have to substitute after the fact. Okay, so with quotient rule all listed out already, okay, we can go ahead and see that the second derivative, okay, so it's going to be like a low derivative of a high, so this is going to be 3y squared minus x, derivative of the numerator, so it's dy over dx, again, done implicitly. Then we subtract it with the numerator, so it's just y multiplied by the derivative of this down in the denominator. So dealing with chain rule is going to be 6 times y dy over dx. Again, the derivative of y is going to give us that first derivative, not 1, but subtracting by x would give us 1, all divided by the entirety of the denominator, all that squared. Okay, so with this line of work, we will then need to substitute back for both of the dy's, because in that case we can get everything just in terms of y and x right there. So with this, we can continue our line of work. So we get all of 3y squared minus x, then multiplied by dy over dx, which is the y over 3y squared minus x, minus y times all of 6y multiplied by y over 3y squared minus x, all that subtracted by 1, all this now divided by the 3y squared minus x, all this squared. Yep. A little bit messy, but still something that we should still be able to handle. We don't necessarily need to solve for any more of this, we just need to go and evaluate, right? So we need to evaluate this at the point -1 comma +1. So all we do is a little bit of plugging in, making sure everything is where they need to be. -1 on the x, +1 on the y. So it's 3 times 1 squared minus a -1. All this multiplied by a +1 divided by 3 times +1 squared minus a -1 minus y. Oh, minus y is minus a +1 multiplied by 6 multiplied by 1 over 3 times 1 squared minus a -1, and then all of this now subtracted by 1. This divided by 3 times 1 squared minus a -1, all of that squared. Okay, so all we need to do now here is just a little bit of evaluation, and that will be it for this. So this will give us a +3 plus 1, so giving us a +4 right there. Then 1 over 3 plus another 1 is 1 over 4. Okay, then subtracting it by, the 1 will cancel out with that, so it'll be a 6 multiply all of 1/4. And then subtracted by 1 all over the entirety of 4 squared. Okay. So with that little bit of evaluation, we get a +1 minus a 6 over 4, and then subtracted by 4 over 4 will give us a +2 over 4 divided by 16. So 1 minus f will be 1/2 divided by 16, giving us a +1 over 32. Okay. And that will do it for this exam. Alright, so let's go ahead and see how we scored. Again, that concludes it for problem number 6 and the rest of the exam. So let's go back to problem 5 and we shall see how we scored overall. Okay. So let's go ahead and take a look at how this answer key will look up here at starting at problem number 5. Again, we have that graph of f prime set up right there. Okay, and we want to see the relative maximum for this part. Okay, so the only one, of course, is that because the first derivative changes from positive to negative at x equals -2. Again, as you can see, we go from positive down into a negative at the -2 mark, as shown there on the graph. Right. Again, as we stated ourselves, again, that f prime of x crosses from positive to negative at only x is equal to -2. Right. That is going to be both the reasoning and our answer shown 2 out of 2 correct for part A. Okay. Then onwards to part B, right? They want to see the open interval from -3 to +4, which is both concave down and decreasing. Okay. With our work needing to show that, again, that we have the first derivative decreasing and negative on those intervals, right? As we show, right? Concave down means that the second derivative must be less than 0, or in this case, the first derivative is decreasing on that graph. And of course, with the regular decreasing, that means the first derivative is less than 0 as well. So both of those cases must be true for this to be involved. That means we get the intervals from -2 to -1, and then +1 to 3, both of which were exactly as asked for, right? Our reasoning is good as well as our answer, so that's 2 out of 2 correct for part B. Okay. Then going on to part C, they want to see where we have points of inflection for the graph of f. Okay, point of inflection, of course, means that if we have the first derivative, right? Again, in this case, they say decreasing, increasing, but in any case, though, we already told us that we have the horizontal tangent line, right? Marks on the, or the maxes and mins on the first derivative, which is gonna match the same thing as well, right? For those points, right? As our reasoning, again, we have our answer at -1, +1, and 3, as was stated at the first part right there that we've had to deal with. Okay, right? Again, yeah. So we have -1, +1, and +3. Again, all of which are represented with those horizontal tangent lines at exactly those points. Okay. Lastly, at part D, again, they wanted to see where we can write those integral expressions for finding f of 4 and f of -2, as what they wanted there. Okay. So because we can list them out with fundamental theorem, right, that the integral is going to show that, right, for any sort of point that we can have listed out as the difference of those 2 points as a result of the integral of the first derivative, right? F of 4 can be isolated as f of 1 plus the 1 to 4 f prime of x dx, right? Okay. And it looks like they actually want us to find the actual results. Okay. Yes, because they did give us the areas. Okay. So we do have the expressions, but it looks like we missed some points, unfortunately, because we did not keep in track that we actually had the areas going from 1 to 4. So because f of positive 1 is going to be already is already equal to 3, so it's going to be 3 plus the 1 to 4 integral. Again, that was already given by the area going from 1 to 4. Again, that's something that I overlooked. So that's going to be plus 12, so that gives us a positive wait a minute. Yeah, positive what? We're going from 1 to 4. Why is that negative? What is happening here? Oh, that's right. Okay, that's right. Because so it is going to be negative because this entire area underneath here again is in negative 12. Right? The area itself is 12, but because underneath the axis, when we do the actual definite integral, it's going to be negative 12, giving us a negative 9 as a result. And then for f of negative 2, right? F of 1 was positive 3, and we're subtracting it by a negative 9, giving us a positive 12 as an area. Again, the area between negative 2 to positive 1 was already given as 9, so that needed to be shown as a result. Unfortunately, that's going to miss us some points, but that's going to be 2 out of 3 because we did set everything up as we needed to, just did not evaluate when we should have. Okay. Unfortunately, that's a dropped point. Hopefully we can finish this off properly with 8 out of 9 on question number 5. Let's see how we can finish this up with question number 6, and we will be done with this exam here. Okay. So with question number 6, we have that curve, right? And we have that first derivative, dy over dx, as shown right there. Okay. So with question A, they're asking for the line tangent at a specific point, right? Meaning that we have to set them up as the y is equal to, right? Y is equal to x minus h plus k. So again, by plugging everything in and solving for that first derivative on the slope, right, at the negative 1 comma positive 1, we do get 1 over 4 right there with everything plugged in exactly, right, with the 1/4 of all of x plus 1 on the outside. That gives us 2 out of 2 correct right there. Okay. And then they want to go next in to see where all the points of line tangent is vertical, right? So again, we have to set up that understanding that for the first derivative, we need just the denominator to then be equal to 0. So by running through that, right, we can get the expression that x is equal to 3y squared. But because we need to see if that still fits on the curve, we had to plug that back into the curve itself. And so we get the point y is equal to negative 1. And of course, the x point at x is equal to positive 3. So those coordinates do match, right? Again, by setting first that equation, then putting it back into the curve, and then getting the actual answer of the coordinates gives us all 3 out of 3 correct for this. Okay. And then lastly, we need to go and do the second differentiation of the dy over dx at a specific point, right? So by running the quotient rule, right, this is going to be the 3y squared minus x, all shown right there, times dy over dx, subtracted by y, times the 6y times dy over dx, again using chain rule to keep that 1 in mind, subtracted by 1, all divided by 3y squared minus x, all that squared, right? So this is going to be both 2 points to do that implicit differentiation. Then substituting everything else back in there, right, with that 1/4, of course, going to be there for the dy over dx, right, where that was going to be shown in our line of work right there. And our answer ending up at 1 over 32, right, after plugging everything in. That will give us all 4 out of 4 correct for part C. All right, good that we course corrected right there with everything correct on number 6 there. So this is going to be 9 out of 9 correct for question number 6. So with that in mind, we get the total score of missing 5, so that's unfortunately 49 out of 54. Percentage-wise, that's going to be, if we took care of that, so 49 out of 54, that's going to be exactly 90.74%. Okay? So percentage-wise, not the best, as there's one problem that really messed us up a little bit, but nonetheless though, this is exactly the kind of practice that we need to keep up with everything that we need to do. Again, 2 of which should have been simple mistakes that could have been easily avoided. But nonetheless though, that will conclude it for the 2015 free response questions. Again, we're actually working on this channel to finish up our last video on calculus. And that should conclude it for all of our AP Calculus, as again, the exam is only in 2 weeks, and we'll be moving on to other subjects on our main YouTube channel. So once more, again, thank you all for coming in to see this stream. Again, this will be fully recorded on our channel itself, again, on the live section. So if there's no other questions, again, you can email us directly at the labcoatmath@gmail.com, or you can, again, send anything else through the chat. So nonetheless though, I'll be doing it here for today, and we'll be back again next week, or this upcoming Thursday, sorry, for another exam packet. So thank you all for tuning in, and we'll see you again on Thursday.